This is the Calculus Building. I'm Gregory Carlson. Let's look at another example of finding a limit at a point. Here it says, use a table and/or graph to decide whether the limit exists. If it does, find the value. So you can see here we've got an absolute value function, and we're going to try to find out if the limit exists. As you know, that is not as simple as plugging in the number 2 and finding the answer. Even though that works most of the time, that is not really what a limit is. A limit is something we approach. So let's make a table, and we're going to approach the value 2, and as we know, the actual value at 2 does not matter. So what I'm going to do is, let's make some new values. Let's do, I don't know, let's do 1.9, 1.99, and 1.9999. So we're going to get really close to 2 from the negative side. And approaching it this way, let's try doing the values 2.1, 2.01, 2.0001, and 2. Let's see, I've done one too many on this side, but that's okay. 2.0001. All right, so let's plug those values into our function and see what we get. So if I plug in 1.9 into this, let me grab my calculator, and we will do 1.9 times 3. We get that number right there, minus 7. And we know that when we take the absolute value of that, it turns it positive. So when I plug in 1.9, I get positive 1.3 because we took the value, absolute value of it. How about 1.99? We do 3 times 1.99 minus 7. We get the value negative 1.03, except it's positive because we took the absolute value of it. And now let's plug in 1.9999 because we're getting really close to 2, times it by 3, and subtract 7. And we turn it, absolute value makes this positive, so it'll be 1.0003. So it looks to me like we're approaching 1. And certainly we could do even more. Let's do 1 point just for fun, 9999999. And let's multiply it by 3 and subtract 7. It seems to me when we take the absolute value of that, it turns positive. So it seems to me that we're approaching 1. So I would say it looks like the limit as x approaches 2 from the negative side. And by the way, if you don't want to write f of x, you can write the actual function right there. Absolute value 3x minus 7 absolute value. That'd be fine. So as we approach it from the negative side, it sure appears to be approaching 1. Let's see how we approach from the positive side. Let's plug in 2.1 times 3 minus 7. We get negative 0.7. Let's try plugging in 2.01. Oh, and once again, here I am. Take the absolute value of it, which will make it positive. So let's try plugging in 2.01 times 3 minus 7. We get positive 0.97. That makes me feel like I did something wrong here. Let's try that again. 2.1 times 3 minus 7. No, that was right. Okay. Let's try 2.001. Or actually, I've got 2.0001 times 3 minus 7. And turn that positive, and we get 0.9997. So, seems like and remember, absolute value will make it positive. So let's try 2.00, let me clear my calculator, 2.000001, a little bit higher than 2, times 3 minus 7. And turn that positive thanks to the absolute value. It's going to be 0.999997. So you get the idea. We're getting closer and closer and closer to 1 from the positive side as well. So therefore, the limit exists, and the limit as x approaches 2 of our function, it appears to equal 1. So let's actually plug in 1 into our function and see what it equals, just for fun. I'm sorry, plug in 2, as x approaches 2. So as x approaches 2, let's plug in a 2 and see what we get. So sure enough, our function actually does equal that value. So that's nice to know, but it doesn't really matter. As we approach from both sides, we get equal to 1. So let's actually graph it. The way you would graph this is, as this is an absolute value point, and the minimum value is when this equals 0. So let's find out when that happens. Let's set 3x minus 7 equal to 0. Add 7, add 7. 3x equals 7, divide by 3, divide by 3. So if x is equal to 7 over 3, which is equal to 2 1/3, that's our minimum value. That's when the absolute value function hits 0. And then from there, we go up in the positive and negative direction with the slope of 3 over 1. So as we go this way, it's going to be up 3 over 1. So 1, 2, 3 over 1. So kind of a narrower absolute value function. And as we go this way, it's up 1, 2, 3 over 1 with a slope of negative 3. So about right there. So there's roughly, that's just a sketch, but there's roughly the graph of our function. And as you can see, at the point of 2, we are equal to 1. As we approach that value 2 from the negative side and the positive side, you see that it equals 1, and there we go. So as you can see, this takes a lot of work. It takes a lot of work to make these tables and figure out if the limit exists. So wouldn't it be nice if we could just get away with plugging in the value? Well, you're not supposed to, but let me tell you that there are some functions that tend to behave. And I put the words behave in quotation marks. So functions that behave are linear functions, like for example the function 3x plus 4, or the function f of x equals, I don't know, 1/2 x minus 8. Those functions behave. And what that means is they're continuous. And I'm going to define that in a future video. What that means is, if you want, you can go ahead and plug in any number, and it's going to turn out that that's what the limit is as well. Same for polynomial functions. Say you have the polynomial function 5x to the third minus 6x squared plus 9x minus 7. Even though we have a lot going on in this function, it's going to behave. The value is going to equal the limit that it's supposed to be. Square root functions, where they exist, also behave. So as long as the function exists, because as you know, a square root function kind of looks like this, like here's roughly what the graph of that would look like. Where that square root function exists, it's going to behave. It's going to be continuous. And as we just saw, our absolute value function also behaves, that we did in that previous example. So if you have any function that looks like this, if the graph exists, so we don't have any limits over here because there's no graph to look at, okay? If the graph exists, you have my permission to go ahead and plug in the point and see what the limit is going to be. Okay, isn't that nice? Two functions that misbehave, or that are not continuous everywhere, would be hyperbolas, because as you know, as we saw in an earlier video, if you have a hyperbola, and if that hyperbola approaches an asymptote that are approaching it, one going to infinity and one going to negative infinity, that's not continuous. That does not have a limit at that point right there. Another example of something that doesn't behave is a piecewise function. So check out this function. We can see that this function has some gaps, so there's going to be no limit right here because we're approaching two different things. No limit right here because we're approaching two different things. So there are some examples of functions that misbehave. So again, if your function looks like one of these, you have my permission to just plug in the point and find the limit. Please be aware that a limit is not the same thing as continuous. I'm going to define continuous very soon. I hope this example makes sense. I hope you appreciate the work it takes to find a limit. And again, I hope you appreciate that the value at that point doesn't matter. It's what we approach. In the next video, we're going to look at what a limit at infinity is. See you there.